So this next example will allow us to review some of the basic rules from differential calculus, as well as examine the differential relationships between charge and current, which we discussed in the course materials. So as you'll see in the problem description, we're given that the total charge entering a terminal in a circuit is given as 5t times the sine of 4 pi t millicoulombs, and we're asked to calculate the total current at t equals 0.5 seconds. So the best approach to take in this problem is to first find an expression for the current at any point in time, and then use that expression to evaluate at the specific time which we desire. In order to get the expression for the time-dependent current, we need to utilize the fact that current is nothing more than the instantaneous rate of change of the charge function. This is a differentiable function, particularly if we look at it, it's a product of two functions. We have a first-order polynomial or linear term, 5t, and we have a sinusoidal term, 4 pi t. Therefore, in order to take the derivative of this product of functions, we need to employ the product rule. So I'll rewrite the given quantity specifically as the product of the two functions which we mentioned. Now, as you notice, we're leaving the units, millicoulombs, off to the end, which is okay. We'll deal with that prefix when we get there. Recall that by the product rule, if I have two functions, say f of t, multiplied by another function, g of t, then the derivative, symbolically, will simply be the derivative of the first function times the second plus the first function times the derivative of the second. Now, in this particular case, if it helps, you can actually write out the individual derivatives. This is a pretty trivial example, so we'll simply do it in our head. If f of t is a polynomial type function, 5t, we can use the power rule in order to determine that its derivative is simply 5. So we'll have a quantity 5 multiplied by sine of 4 pi t. Now we leave the function f of t alone, 5t, and we need to multiply by the derivative of the second function, which is the sinusoidal function. Technically, the second function involves another derivative rule, particularly the chain rule. Recall that the outer function, sine, has a derivative of cosine. However, we have a linear function inside the argument, this 4 pi t. So that will give us an additional factor corresponding to its derivative, 4 pi, multiplied by derivative of sine is cosine. Leave the argument alone, 4 pi t. So that gives us a final product of 5 sine 4 pi t plus 5t times 4 pi cosine 4 pi t. And I guess, looking back on it, I actually didn't make any simplifications there. Probably helps to multiply the coefficients together just to make it a bit simpler. Of course, 4 pi times 5 would give you 20 pi t. And now, just as a bit of review, since it is one of the content items within the body of knowledge relevant to the exam, notice that both of these sinusoidal functions, both the sine of 4 pi t and the cosine 4 pi t, they share the same frequency characteristics, particularly the radian frequency in both cases is 4 pi. And recall that the radian frequency can be expressed in terms of the frequency in hertz as 2 pi. So that's going to imply that these two waveforms repeat at a frequency of 2 hertz, meaning that the period of repetition is just the inverse of that, or 0.5 seconds. Now, if you notice, 0.5 seconds is in fact the time at which we were asked to evaluate the functions. Therefore, we're simply evaluating them after an entire period of repetition. Recall that the sine wave itself starts out at 0, therefore after a period it will also take on a value of 0. You could put that into your calculator if you wish and verify that way. In the second term here, I'm going to have 20 pi times that 0.5 factor. Recall that the cosine function starts its oscillation at a value of 1 after an entire period. It, of course, would be back to 1. Therefore, my final answer is simply going to be half of 20 pi, which would just be 10 pi. Now, be careful with that. What would the corresponding units be? Well, that prefix or order of magnitude, milli, that I had originally, that certainly hasn't went anywhere. So I'm still going to have a times 10 to the negative third. Now, when I take a derivative of coulombs, by definition, a coulomb per second is an ampere, and probably more conventional to write 10 to the negative third in terms of its prefix. 10 pi milliamps exactly. If you wanted to approximate that to 4 significant digits, that would be 31.42 milliamperes.